Hello everybody, Lab 1 by Yakubovich. In the introduction, the purpose of this lab is to demonstrate Newton's first two laws. Newton's first law is if net force is equal to 0, then velocity is constant. Newton's second law is that force equals mass times acceleration, in other words, m times a. So these are my two models. When conducting this lab, I pushed a volleyball across a rug. I took this video and then I utilized a tracker application and put the ball in an axis, and by each frame I plotted a point of mass, and by doing this I also gave it a scale reference and was able to obtain a position versus time graph, and I was able to obtain these coordinates. Based on this, I was able to calculate an average velocity, and I was able to create a more accurate position versus time model, not accounting other factors, through the glow script v Python. The introduction, fundamental physical principles. We know that final position is equal to initial position plus velocity times delta t, and then we also know that final velocity equals initial velocity plus f net over mass times delta t. In this experiment, we know that f net is equal to 0, so there's a constant velocity. As part of the introduction, to preview the results, so we can see that these two experimental and modeled are very similar lines, and the reason for this is because the experimental has other factors that kind of affect the line to not to be extremely precise, and could be air resistance to friction, and it seems to be that Newton's first laws have been proven to be true. So the assumptions that we make is that the f net is equal to 0, so there's a constant velocity and acceleration is 0. No forces of friction or air resistance. The system is the volleyball. The surroundings are the rug and the air and the environment around it. So the initial conditions, f net is equal to 0, the volleyball is already moving, so there's an initial velocity, and we start at time equals 0. So the coding details in VPython are over here. So in specifically, the ball position is the ball dot pause is equal to vector 0, 0. This is because it starts at 0 position. Ball dot velocity, this is the initial velocity, and this was calculated by getting an average velocity, and this was done by final position minus initial position over time. Here there's a while loop, and the loop continues to go until 1.268 seconds, which was the last moment that we saw that the volleyball was moving. We know that f net is equal to 0, therefore the vector is 0, 0, 0. As I previously defined, ball dot velocity is equal to ball dot velocity plus f net over ball dot mass times delta t, and we know that f net is equal to 0, so that final ball velocity is equal to initial ball velocity. Over here, ball dot position is equal to ball dot position initial plus ball dot velocity times delta t. So in this while loop, the ball position is incremented over a period of time, and therefore the position versus time graph will be increasing, and there's a constant velocity. So in this experimental and modeled position, we see that they are very similar. There are a couple differences, and this could be due to other factors such as air resistance and friction. The experimental graph does not we did not account for external factors that perhaps could be preventing the velocity from being constant, such as air resistance or friction, and there could also be human error in obtaining this data, and therefore the modeled is more precise and the experimental has other factors associated with it. Sources of error, as I previously said, perhaps using the tracker application wrong and plotting the points of mass incorrectly, perhaps creating an unstable video, or maybe even environmental factors, or such as friction, air resistance, and not a perfect constant velocity maybe. So in what ifs, so if we flip the axes, the speed would remain the same, but the velocity would become negative. This is the only thing that would change. Our observations were pretty accurate to the computational model. However, is it possible for us to say how many pushes and pulls in the force are added together to give 0? Due to a lack of sensors, we cannot actually say what forces or how many push and pulls there are for this. And for us to actually answer this question, we'd have to utilize some kind of sensors to identify the forces acting on it on all directions. And as a result of this, no, we cannot, since we do not have sensors telling us the direction of each force. Thank you, everybody. This is Ivan Yakubovich.